X is a continuous, uniformly distributed random variable on the interval from 0 to pi over 2. And we've got a transformation. Y equals h of x equals sine of x. So y is going to be a new random variable whose values that it can take on are the sines of the values that x can take on. So if x goes from 0 to pi over 2, you plug that in numbers like that into the sine function, you're going to get numbers out between 0 and 1. Okay, those are the possible values for y. Part A, as always, use the CDF method to show that the PDF has a certain formula. So let's confirm that. That hopefully was the easiest part of the problem. But you do need to figure out the CDF of X first. But being uniform, hopefully that wasn't too much of a problem. X is uniform on the interval from 0 to pi over 2. And it's okay if you just wrote down the CDF right away. But if you want to write down the PDF first, so piecewise function, say, that means the PDF is going to be 2 over pi when x is between 0 and pi over 2, and 0 otherwise. I'll abbreviate otherwise as just OW. And that'll mean the CDF, capital F. Well, if you want to be extra careful about it, it's technically 0 if x is less than or equal to 0, 1, not 0, if x is greater than or equal to pi over 2, and it's the integral of 2 over pi with respect to x when x is between 0 and pi over 2. In other words, just multiply that by x. Should I add a plus c to integrate that when I integrate that? Should I put plus c in there? I hope you didn't. C is 0 because you want capital F of 0 to equal 0. That's why. And you want the right hand, you want it to be continuous in this case. You want the right hand limit as x approaches 0 to be 0. So this quantity needs to be something that goes to 0 as x goes to 0. So that's the CDF for capital X. Y is the sine of capital X by a transformation capital H. I called it capital H to kind of match the capital H in chapter 4 of the book in the expected value formula. Could have called it little h, but whatever. That's the sine of X. We want to find the PDF of Y. Use the CDF method. First find the CDF of Y and then differentiate it. As always, it's this. And yeah, this will be 0 when y is negative, and will be 1 when y is bigger than what? Pi over 2? Go ahead and say it. 1 when y is bigger than 1. So this is only something interesting when y is between 0 and 1. Assume y is between 0 and 1 to make it interesting. I mean, yes, this equation still works right here when y is less than 0 and when y is bigger than 1. And I guess this equation still works there. But the next one, when I take the inverse sine of both sides in the inequality there, I really should be assuming y is between 0 and 1. Certainly not bigger than 1, because I hope you remember you can't plug something bigger than 1 into the inverse sine function, at least if you want a real answer. You actually can plug it into the inverse sine function when you allow complex numbers, strange as that may seem. Mathematica, what's the arcsine of 2? Approximately 1.57 minus 1.32i. Yeah, all sorts of weird things happen when you allow complex numbers. It's not a typo there. Anyway, for us, you can't plug something bigger than 1 into the inverse sine function. You can plug something between -1 and 0 into it, But as far as ultimately simplifying the way we want to, since x is between 0 and pi over 2, y is going to be between 0 and 1 anyway. So take the inverse sine of both sides. And the inequality does stay the same direction, less than or equal to. If you had to give a reason for that, do you think you could give a reason for that? Why does the inequality stay the same direction? Do you ever think about why? I mean, you know that when we multiply or divide by a negative number, you know the inequality changes direction. Why does it not change direction when we, for example, apply the inverse sine function? Anybody ever been told why or remember why? Has to do with the nature of the graph of the inverse sine function. It's always what? What's my hand doing here? It's always increasing. If you don't remember the graph, well, here it is. That's the graph of the inverse sine function. Its domain is -1 to +1. It's the reflection of a piece of the sine graph about the line y equals x. I'm not drawing the sine function, but maybe you can imagine it. And its outputs are between -pi/2 and +pi/2. Anyway, it is increasing, so the inequality can stay the same direction. And this is capital F sub x of the inverse sine of y. And I guess here's where I'm really using the fact that y is between 0 and 1 fully, in saying in that case, the inverse sine of y is between 0 and pi/2, and therefore I can use this formula and get 2 over pi times the inverse sine of y. Y is between 0 and 1. It would be 0 when y is less than 0 and 1 when y is greater than or equal to 1. And little f is the derivative of capital F. And going back to your Calc 1 days, take the derivative of inverse sine, you'll get 1 over square root of 1 minus y squared. So you get the answer in the exam. It looks like that. Let's go ahead and use Mathematica to check that this does seem to be a PDF. It should integrate to 1, right? Oops. 2 over pi times the square root of 1 minus y squared. That's actually a pretty easy integral to do because antiderivative is going to be the CDF. Technically speaking, it's an improper integral. It's got an impropriety at y equals 1. Technically speaking, it's a limit of integrals that look like this when as b approaches 1 from the left. But those integrals, when you do them, all involve 2 over pi times the inverse sine of b. In fact, they equal 2 over pi times the inverse sine of b. Inverse sine of b as b goes to 1 from the left approaches pi/2. 2 over pi times pi/2 is 1. So technically it's an improper integral, but you didn't have to check this anyway. Oops. All right, so that is the answer for part A. Part B, show work by hand in 2 ways. That the expected value of y is 2 over pi, first by doing an integral involving the PDF of x, and second by doing an integral involving the PDF of y. We're after the expected value of y. Based on the PDF of x, that means go back to chapter 4 and use the generalized expectation formula. The expected value of a function of a random variable. In this case, that's the expected value of the sine of x. Right? And the generalized expectation formula says to integrate whatever that function is, in this case, the sine of x, times the PDF of x. over whatever the domain is for the PDF of X where it's positive. That domain is 0 to pi over 2. And the formula for the PDF when X is between 0 and pi over 2 is 2 over pi. So that's a 2 over pi. So you get 2 over pi times integrate sine, you're going to get negative cosine. So you get negative cosine of pi over 2 minus negative cosine of 0. Cosine of pi over 2 is 0. Cosine of 0 is 1. 2 minuses make a plus. 2 over pi is the answer. So that one's fairly easy to do, but you got to know what to do. You can also do is an integral involving the PDF of y. This thing here. Integrate y times the PDF of y is what you should have done over the interval where the PDF is positive 0 to 1. This should give the same answer. But this was the one where I said, technically speaking, if you're going to be, well, you could do it just by guessing the antiderivative or figuring it out on the side. But if you're going to be careful about this as a definite integral, you should do a substitution. U or W equals 1 minus y squared is a good substitution to do. And dw is negative 2y dy, which is almost up there except for no minus sign. So it looks like we get negative 1 over pi. I brought the 1 over pi out, and I also brought a negative sign out. Ultimately, w to the negative 1/2 dw. You should change the limits of integration, though. You got to be careful when you do this. Use this equation here. When y is 0, w is 1 minus 0 squared is 1. And when y is 1, w is 1 minus 1 squared is 0. Huh. Is that wrong? No, that's actually right. However, you can switch them back to going from 0 to 1 and then just negate the negative sign to get a positive sign. This is the same as this. And yeah, this is still technically an improper integral. This is, this is 1 over square root of w. There's an impropriety and a vertical asymptote at 0. So technically speaking, it's a limit of proper integrals, but once again, you can do it without bothering to write the limit sign. And it works out pretty nicely. Integrate w to the negative 1/2, you get w to the positive 1/2 divided by 1/2. Dividing by 1/2 is the same as multiplying by 2. In the end, you get 2 over pi still. It's nice to see you get the same answer. So I hope with, me telling you what the answer was, that even if you were confused at first, you were able to figure this out. And it is confusing. It's all these different variables all over the place, as part of the confusion. But if you go carefully and think about concepts and what we've learned, I hope most of you were able to get this. I would like to show you again a Mathematica animation that's going to illustrate this stuff pretty nicely. Let's keep going before we do that. Part C, find the mean and standard deviation. No, find the standard deviation. Any way you want, effectively. One way might be easier than the other. I was unsure if, when I was first writing this, I was thinking one way might be significantly harder than the other. But then I actually tried them both this morning. And one way is harder than the other because it just seems harder, but it's actually completely equivalent to the other way in terms of difficulty level because of a substitution you can do. It's just that the substitution is not so clear. Of course, to find the standard deviation, we got to find the variance first. And to find the variance, we got to find the second moment first. So you could find the second moment of y, which is the hardest part of the problem. And the way I was thinking of doing this that would be easier is to use the generalized expectation formula to say this is the same as the expected value of h of x squared. In other words, the expected value of sine squared x. And doing that integral, although that's still not super easy because you got to integrate sine squared. If you use the table or use Mathematica to do that integral, it's okay to a certain degree. Did I say by hand? I did say by hand. The integral ends up being the integral from 0 to pi over 2 of sine squared x times 2 over pi dx. That's the PDF of x right there. You can do this either by doing integration by parts a couple times, or it's okay if you look that up in the table, or use Mathematica to just do this integral symbolically, at least just if you start it by hand like this. I like doing it by using a trig identity. And this is what I teach my Calc 2 students if you're tutoring them in math lab. Sine squared x is the same as 1/2 minus 1/2 cos 2x. Just a trig identity to say those are equal. If it were cos squared x, by the way, this becomes 1/2 plus 1/2 cos 2x. That's the way I teach my Calc 2 students to do this one, because that's fairly easy to integrate. Integrate 1/2, you get 1/2 x. Integrate minus 1/2 cos 2x, you'll get minus 1/4 sine 2x. Sine of 2x evaluated at both 0 and pi over 2 is 0, right? Sine of 0 is 0. 2 times pi over 2 is pi, sine of pi is 0. So the sign here really doesn't affect anything. The only way you get something non-zero is when you replace x over here with pi over 2. So you get 2 over pi times 1/2 times pi over 2 is pi over 4. 1/2 is the second moment. Before doing the variance and standard deviation, let's think about the second moment with the other method. It looks harder, but it really ends up being equivalent if you do a trigonometric substitution. So if instead you do it using the PDF of y, kind of like this, except make a y squared there. Then you're integrating 2y squared over pi times the square root of 1 minus y squared, which looks really hard to do. And, you know, an ordinary substitution that you might try, w equals 1 minus y squared, doesn't seem to help much because it's a y squared up there. But a trig substitution is the way to go here. I don't know if you remember trig substitutions from Calc 2. If you're a tutor in math lab, you may have helped some students do them. Let y, because of the square root of 1 minus y squared here, it's a good idea to let y equal, say, sine theta. I'll use a theta, but I could have used an x. dy is cos theta d theta. The y squared up there can be replaced with sine squared theta. The y squared in here gets replaced with sine squared theta. And then dy gets replaced with cos theta d theta. Do need new limits of integration, use this equation. When y is sine theta, theta is inverse sine of y. So when y is 0, theta is the inverse sine of 0, which is still 0. But when y is 1, theta is the inverse sine of 1, which is pi over 2. This is starting to feel familiar. It simplifies things. Once you do the trig substitution, they're equivalent in difficulty. That's a cos squared theta. Technically, the square root of cos squared theta is the absolute value of cos theta. However, theta is between 0 and pi over 2. So cos theta is positive. So this is the same as cos theta. And that means the cosine theta there cancels with the cosine theta there. And yeah, I'm doing the exact same integrals before. Integral from 0 to pi over 2 of 2 over pi sine squared theta. It's the exact same. You get 1/2. Sorry. It's nice to see it work out. I'm expecting most of you did it this way. And maybe you used integration by parts, or if you use the table or Mathematica to do the antiderivative, that's fine. Right here with this sine 2x, you may have gotten 2 sine x cos x instead, because that's your trig identity. You may have gotten that. Maybe doing integration by parts twice gives you that. 2 sine x times cos x. You still get the same answer. So the variance then becomes the second moment, 1/2 minus the first moment squared. The first moment was 2 over pi, right? So that'll be 1/2 minus 4 over pi squared. Get a common denominator of 2 pi squared. And there we go. The standard deviation is what it says is the square root of that. And that can be written as I have on the paper, square root of pi squared minus 8 divided by square root of 2 times square root of pi squared is pi. Then you simulate it. So let's look at Mathematica now. So I'm using random variate to do the simulation. Did I say 100 data points? Sample size 100. To get the y data, the transform data, you can map the h function onto the x data. I add a little bit more in here just to see. Ignore this at the moment. Just to see a graph of the x data. Fairly uniform. What about the y data? I didn't require you to do this. Not as uniform, though it's not completely obvious that it's not as uniform. They both look relatively uniform. But the y data, technically speaking, is going to be denser over here. Let's try to rerun the simulation and see if it's more obvious. Okay, there it's seeming fairly obvious that the data is pretty dense over there when y is close to 1. And the PDF of y gets higher as you get close to 1. In fact, you got a vertical asymptote there. These numbers matching about 0.685 and 0.294. Reasonably close to those. So it's good to see the numbers matching, but I also had some fun here making a visual for this transformation. So here's the X data from the uniform distribution from 0 to pi over 2. There's the graph of sine of X. X going from 0 to pi over 2. The outputs go from 0 to 1. And this will transform the X data into Y data. And it's the fact that the graph approaches a horizontal line here for the tangent line as X approaches pi over 2, that the data can get so dense near 1. And here's a 3D picture of it. Showing exactly the same thing with the PDFs of X and Y superimposed. The PDF of X is this horizontal line, that's the uniform distribution. The PDF of Y is this pink curve. Notice it's got a vertical asymptote as you approach 1. So here's the transformation in a higher dimensional space. The fact again that this graph approaches infinity as Y approaches 1 means technically speaking, the data, you might say, gets denser and denser as you approach 1. Of course, you really only see that, so to speak, when you've got, say, thousands or maybe millions of data points. Would you really see that clearly in terms of measuring density of data? Okay, so I had fun with that. I'll share that with you if you want to play around with it. Okay, I had to experiment with trying to get it to visualize it this way. But I think it's kind of neat that you can.